Welcome everybody to week 4, day 2. I just finished the HIO Epic Mega Game Jam Thingy Me Bobby, and so Ada designed this game. We uploaded it. And we'll see what people say. It's a pretty small game. Like you can beat it pretty quickly, but it's kind of fun. And what we have right now would be enough for Ada to on her own just build more stuff and more monsters and things like that. Okay. Yeah, I do like the outline effect of the skeletal meshes and things like that, and yeah, it worked out. It worked out all right. Okay, so if you want to learn how to do that kind of stuff, take IS 50A or 50B if you're in 50A. If you're in 50B, I'll teach you. Okay, so let's learn some new stuff. We're going to learn counting. Let's learn some counting stuff. Set theory. Okay. So, last time I gave you sort of a brief overview of set theory. Today we're gonna get into it. So, terminology. A set is a collection of elements. A set is filled with things, and these things can be kind of anything. They can be numbers, like integers. They could be cards or cars, and basically, with some very few exceptions, you can kind of describe a set however you want. Like you don't even have to know what's in it exactly. Like I could say the set of all hydrogen atoms west of the Mississippi. You know, like I don't know how many hydrogen atoms there are or where they are exactly, but you know, I can make a set out of it. Basically anything I can say in English, you know, it's a set. And every hydrogen atom is either part of that set or not part of that set. So, and if you're not a hydrogen atom, you're definitely not part of the set. So, there were some important caveats that came about. They used to just allow you to kind of make a set like, you know, any way you wanted, and then after Bertrand Russell and some other people kept discovering paradoxes that came about. For example, Russell's paradox says, make a set of all sets that don't include themselves. Right? So is it a member of its own set? I don't know. So that sort of actually destroyed math. So around the 1900s, there was this thing called the foundational crisis in math, and it was kind of a big deal because like everybody thought math was like this really certain thing, and when it came down to it, like nobody actually knew why math worked or if it worked or you know if there was any sort of like formal verification that math actually worked. We knew that in practice it worked, but you know, were we just being lucky? You know, that kind of stuff. Am I standing? I am standing. Yes. So they have since revised the sort of unlimited notion of sets, and there's actually a pretty good comic book on this, which was written by a former professor of mine, actually, or partly written by Logic Comics. Early Life of Bertrand Russell. Is this the one? Yeah, this is the one. Yeah, okay, Papa Demetrio. Yeah. So that's the story of him making the comic, or no, that's him there. So it's a story of Bertrand Russell and his youth and growing up and stuff like that. So pretty good. You can probably find it pretty cheap. And it talks about how mathematics as a field was sort of placed on firmer foundations as a result of this big crisis. And there's all sorts of drama that took place, like David Hilbert like imprisoning his own son, and Poincare and Hilbert forming opposing schools of mathematicians that would run around like gangs in Paris in the antebellum period, or the mid-war period, I guess, technically. So, actually, no, this would be Belle Epoque period in Paris. So they're meeting at like these Parisian cafes, like arguing with each other over what the basis of mathematics should be. And the long story short is that set theory is sort of nowadays widely accepted to be the foundation of mathematics, which seems weird because they don't teach set theory, right? They used to. It used to be a standard middle school topic. So what I'm going to teach you guys today, feel good. It's what they used to teach in middle school. So terminology wise, yeah, just sets are just collections of things. They don't have any ordering. Something's in the set or it's not in the set. You know, it's a set of all presidents of the United States, right? Technically, I guess there is an ordering to the presidents, but from a perspective of a set, it doesn't matter. Carter is either in the set or he's on the set, right? And this corresponds very much to the set container class in C++, right? You insert things, you see if they're in there. It doesn't preserve order at all. Okay. So if I create a set by saying the set of all models of cars made by Chevrolet in 1981, then the 81 Chevy Citation is in the set. And the 81 Chevy Camaro is in the set. The 82 is not. Do you guys understand? And when you write the set, you can write it any way you want. You don't have to alphabetize it. Oftentimes people do alphabetize it for convenience sake, but if I were to make a set of all the students in the class and I printed it to the screen, it literally doesn't matter what order I printed it. Do you guys understand? Because like you're either, you know, Shahab is in the class. Doesn't matter if I print him first or if I print him last. Does that make sense? Like you're in or you're not in. Okay. It's a binary set kind of, you know. You're either in or you're not in. There's also things called fuzzy sets that have partial set membership. But I don't know if we'll talk about that today. All set? All right. We typically write sets using curly braces. If you've seen curly brace notation in C++, it's pretty much that. So here we have a 1981 Chevy Citation. This was my first car, by the way. And if you're like, wow, I didn't know you were that old, I'm not. The car was that old. Yeah, it was old even when I was in college. And you know, if you're ever wondering if a car is any good, just one easy way of telling is like if it's named after a parking ticket, like it's probably not a good car. You know what I mean? Like it's the citation. Like it's what you get when you park in a handicap spot without a placard. You know what I mean? So yeah, a horrible car. But my grandfather found an old lady in his retirement community that was selling her car for like $500, and so he bought it off her and gave it to me as a graduation present. So it was really nice of him, and I actually drove that car for a couple of years. It broke down constantly, and the old lady who had the car always stuffed her old plastic bags underneath the driver's seat, and I didn't know this until I was driving down the freeway with the windows rolled down. Of course, there's no power windows on this thing, because why would there be? And all of a sudden the wind starts whipping these plastic bags out from underneath the seat, and they're like spinning around inside of the car, and I'm on the freeway, and there's just like these bags flying around like ghosts getting in my face in Ghostbusters or something, and I can't roll up the windows because there's no power windows. I roll up mine, and then I'm like reaching over with like bags blowing in front of my face, like trying to roll up the other windows, and fortunately didn't die, but ever since then I've always checked beneath the seats when I've bought a new car. I've also learned a lot about cars from it, because every time the car breaks down, you learn something new. So that's how an alternator works. That's what happens to your car when the alternator goes out. Good to know. You get to spend a couple days in a not so nice part of LA. That's what happens. Cool. Awesome. No gremlin. Yeah, it's pretty close to like an AMC gremlin. Yeah, and to be fair, it is not. It's not a good car. Yeah. Yeah. Or you have the Pinto. I mean, it does kind of look like this Chevy Citation, honestly. A little bit. So, yeah, my car is an even uglier color than that, though. It's like pasty white / green stripe, two-tone. So here you have the Chevy Camaro, which looks like it's smiling broadly in the front. So both the 81 Chevy Citation and the 81 Chevy Camaro, they're both in the set of cars made by Chevrolet in the 1981 season. Not year, because cars come out a year prior to their, they're all the same car. Feeling better about the Prius. Yeah, the Prius is actually Priuses aren't bad. You're not going to win a drag race in a Prius, but they're not bad. Yeah, my sister drives a Prius, and one of my friends worked at Microsoft and made a lot of money. Like, he owns a condo in Palo Alto. He drives a Prius. Yeah, nothing wrong with that. Although, spent $90 in gas in August. Yeah, I don't know, if you only drove a mile, that's pretty bad. You got to tell me how many miles you drove in August. Yeah, I don't know. It might just be a matter of the Bay Area virtue signaling or something, but they're pretty popular over there. I went to visit an old professor of mine in Palo Alto, and he had a Prius too, so we had to go over to his house when he was on vacation and turn his Prius on or something like that. I don't know. I don't understand how that works. Okay. Average 30 miles. Is that it? Yeah, it's not bad. Yeah, like my sister gets like 40 something. I don't know. He must be driving it pretty fast. Okay, so we typically use capital letters to represent sets. This is just convention. You don't have to, but just convention. So, for example, we could say A is the set of all even numbers, and Z is integers, of course. Then there's something called set builder notation, which looks like this thing here. And we can say we're going to define a set called B. B is equal to, ready for the English translation of this, all X such that X is an element of Z. In other words, X is an integer. And X is greater than 42. Okay. So this is the number 43, 44, 45, 46, infinite set. Okay. And then the things don't have to even be the same type, right? If you want to really confuse people. C is a set containing an int, a float, a imaginary number, a negative number, and Bob. So there you go. Getting 50 miles per gallon. Yeah, that's brutal. Yeah, and the gas prices are brutal also. But we didn't run out of gas. In the springtime, I was broadcasting live and pulled up a CNN article where they said they're expecting your local gas station to run out of gas. And nah, it didn't happen. So suck on that, CNN. Okay. So basically, the rule is, for normal sets, is that everything in the universe, whatever the universe is, the universe might be integers or whatever you're playing with, you might limit the thing. But basically, everything's either in the set or not in the set. Okay? So that's sort of the primary deal with a set. Either something's in the set or it's not. There's no ordering, it doesn't matter. Like, if we put Bob first, like, it would be the same set. Are you guys with me on this? Like, that's the fundamental aspect of sets. Okay, so terminology point number 2. Use absolute value signs to indicate the size of a set. And this is something that students who are perhaps AFK right now and not listening miss. And so whenever I do a quiz and there's like an absolute value, they're like, how do I take the absolute value of a set? And it's like, no. It's not absolute value. I went over this in class. It is the size of the set. Mathematicians love reusing symbols. They love it. They hate coming up with new stuff. So, how many times has I been used for something, Only through context we know it's an imaginary number. X. Many variables have been called X over the years, And so, yeah, absolute value bars are the size of the set operator. So C here has got 1, 2, 3, 4, 5 people in it. So I counted, look, I counted. C has 5 people in it. So the cardinality of the set is the technical term, which is the vertical bars. It's the cardinality. I don't know if you guys know about ordinal and cardinal numbers. Ordinal is first, second, third, fourth, fifth. Cardinal is, it's a little too low. Cardinal is 1, 2, 3, 4, 5. You know what I'm talking about? The difference between first and 1. Ordinal puts things in order. This is first, this is second, this is third. And cardinal is just how many elements there are in a set. Okay, you guys all get that? Absolute value, when applied to a set. Size. Size of the set. Alright, let's go on. So, a general rule, and a pretty obvious rule, right, is that if you can kind of draw a one-to-one and onto correspondence between all the elements in one set and all the elements in another set, the sets are the same size. Do you guys concur? That if I can match exactly one element of one set with exactly one element of the other set, one-to-one and onto correspondence, that these sets have the same size. So if I tell you that set L here of leopards is of size 5, and it has a one-to-one and onto correspondence with sheep, then I know sheep has size 5. Alright, 2 students that are alert. Good. I'm about to blow your mind. So one of the fun things about discrete math is that it leaps back and forth between like trivially, like, yeah, why are you even bothering to tell me this, you know, and like, what? the difficulty fluctuates wildly. So this is the easy part right now. So if you're having trouble with the easy part, please let me know, because this is what's going to explain the hard part. Kind of like when we were talking about modular division, you have to understand modular division in terms of modular multiplication, right? I was wondering why I was relearning counting again. It seems so easy, doesn't it? It seems so easy. Okay. We're not quite there. We're getting there. So the complement of a set, complement of a set is everything not in the set. Okay. So if I define E to be all even numbers and Z, then E complement, and it's written with a little power. This is not to the cth power. Again, math people reuse symbols and terminology all the bloody time. It is so super annoying. You'll not believe how many times I've graded a midterm and a student's like, well, I'm going to take this power to the cth power. I don't know what C is, though, and so I'm just going to do some sort of algebraic... I'm like, no, it's not exponentiation. We just wrote it like that. We wrote it like it was exponentiation. It has nothing at all to do with exponentiation. It's just confusing. Deliberately maybe confusing. I don't know. I'm not really sure if it was deliberate, but it is confusing. So it looks like we're taking E to the cth power, right? No, we're not. Not at all. It has nothing to do with power. Instead, what E to the cth power means is the set of everybody not in E. Okay. So if we're in Z6, in other words, the only numbers that exist are 0 to 5, and we got a set A that's 0 to 3, then the complement of the set is 4 and 5. Do you guys see that? It's like this is everybody not in the set, right? That's one of the reasons why I introduced modular arithmetic first, is that without this you'd have to write an infinite number, and that's kind of annoying sometimes. Okay, so a little bit more terminology. If you ever write a 0 with a line through it, that is not 0. Okay? That is not 0. That means empty set. That means there are no elements in the set. I don't know why they didn't just draw with open, close, curly brace. You know what I mean? Like, where is the pen for this? There we go. So, I mean, I personally, if it was up to me, I would just draw a set that has nothing in it like that, you know what I mean? Like in C++, you just do that. So I'd say like A is equal to that. There's nothing in it. But no, math people like drawing something in it. They like to say if there's nothing in A, then they draw a little null character there. But that's not an element. That's not an element. That's not a thing. If you take the size of A, the size of A here is actually 0. Okay? So there's no elements in A. That's what that means. It's the null character. They didn't explain that in Zybooks. I've been confused on some of the lessons. Yeah, the terminology is always the worst part when it comes to math. Like, legitimately. Like, once you understand the terminology, like the math, not always as easy, but like it gets a lot easier, you know? And so that is not a 0. That just means there's nothing in the set. Okay. So let's talk about intersection and union. Okay. So if I have a set A that is 1, 2, and 3, I have a set B that is 2, 3, and 4. The intersection, which is written with a little wicket character, if PowerPoint would allow it, it's this character here. It's called a wicket, like in croquet. A intersect B, that looks like a hyphen. Let's do that. Okay. A caret, rather. Okay. A intersect B. This means give me a new set, return a set that has all of the elements that appear in both A and B. So for intersection, it's, if you ever see a Venn diagram, right? Intersection is that part there, right? So if you've got, here we've got 1, 2, and 3, and that's A, and then B is 2, 3, and 4. The intersection is 2 and 3. Okay. The intersection is, it is the set of all elements that are in both sets. Both sets. It has to be here and here. So 2 and 3 appear in A, 2 and 3 appear in B. So the intersection is that. So union is represented by a weird looking U. That's not a U. Some people will write it as U because it's really annoying to type this special character for it every time. Word can do it. There's a symbol table in Word, and you can like click around and like find it and stuff. Usually what I do though is I go onto Wikipedia and search for union and copy and paste the symbol. It's faster that way. So, okay. So union is when an element appears either in one or the other, or both. So if we have A is equal to 1, 2, 3, B is 2, 3, 4, then A union B is the numbers from 1 to 4, which I'm not going to write out. Okay. But that's the numbers from 1 to 4. Okay. So intersection is like and, if you want to think of it that way. Right? In computer science, we have and. It's something's true only if both sides are true. With a intersection, if it's in both sets, then it's in the resulting set. And then union is like or, right? If an element appears either here or here, then it appears in the outcome. Okay, so it's like it's kind of conceptually like or in computer science. You can appear in either or place. And then complement is like not, right? So if A is 1, 2, and 3, then A complement is, 0 and less, and 4 and more. There's probably a more technical way of writing that, but whatever. You guys see that? So if we're operating in like Z, right, just integers, then if A is 1, 2, and 3, then a complement is all the numbers less than 1 and all the numbers greater than 3. Right? So 0 and less and 4 and more. You guys understand? Okay. So, what is... Okay. So, yeah, if A is 1, 2, 3, 4, and B is 3, 4, 5, 6, the union is 1, 2, 3, 4, 5, 6, 7. Yeah, the number is 1 through 7. So what is A intersect B? Anyone want to take a crack at that? What is the intersection of A and B? What numbers appear both over here and over here? Yeah. 3 and 4, right? Okay. So, what is the size of A intersect B? What is the size of A intersect B? It's 2. Yeah. It's 2. What is the size of A intersect B complement? How big is that? A union B is 1 to 7. Because A is 1 through 4, B is 3, 4, 5, 6, 7. You don't put 3 and 4 in there twice, right? Because why would you? Either something's in the set or it's on the set. So 3 and 4 do not appear in the set twice. What is the size of A intersect B complement? So if we know that A intersect B is of size 2, right? It's the numbers 3 and 4. Right? We got the numbers 3 and 4 in a set. That's A intersect B. What is the complement of that? We got a lot of 5s in the chat. What is the complement of A intersect B? Would it be infinite with the exception of those numbers? I don't know. Can you do that? Is that allowed? Infinity minus 2, is that a thing? Does it even make sense for there to be infinity minus 2? I don't know. 3? What are the 3 numbers, Tomas? In A intersect B inverted. Are you going with like the 1, 6, and 7? Is that what we're going for? But that's not the universe. The universe is integers. You would have been right if we'd had a limited universe, but our universe is integers. So all integers are possible. So how many integers? Let's put it this way. Let's do this in English. How many integers, because we're doing size, right? We're doing size. How many integers are not 3 and 4? How many integers are not 3 or 4? Five? There's only 5 integers? This is Z. This isn't Z7 or something. Z. Like there's 999, 1000, 1001, 1002, 1003, 1004. There's more than 5. 1005, 1006, 1007. These are all not 3 and not 4. 1008, 1009, 1010. I can keep going. Infinity minus 2. Yeah. Infinity minus 2 doesn't actually kind of make any sense. Because, I mean, I know where you're coming from with that, but it's just infinity. And so that is actually how you write infinity for these kinds of things. It's what's called a countably infinite. That's what that means. And anyone know how you pronounce that? The N0? Aleph? No, nobody was going to go with Aleph on that one. Yeah, that is Aleph, and because there's a 0 there, it's called Aleph Null. And this is actually a fairly famous term in computer science. Aleph Null. It is the size. It's the size of an infinity. It's the size of an infinite set. But it's very specifically the size of certain kinds of infinite sets. Those are like integers, right? So. It's not. They're changing everything. Yeah, it's Aleph Null now. Ton of infinities. Yeah. This is just the most famous infinity. Okay. Did I save that? There we go. Right. Okay. So, A with the union of A complement is just Z, right? Because that's our universe. The size of Z is Aleph Null. That's, you can almost define it as the size of integers. How many integers there are. It's Aleph Null. Okay. Why must they reuse everything? Yeah. What drives a man to neutrality? Alright, one more maybe. Is that it? Yeah, okay. One more bit of terminology, and then we'll be done with most of it. So, subset, and you might hear like people use the term subset in just like casual language use, like, oh yeah, I'm gonna solve a subset of our problems today, or yeah, I'm gonna go take a subset of our to-do list and give it to Bob or something like that. Okay. So it's used in sort of casual language with a similar meaning. And what it means, if you're a subset, that means that you have every element in common with the superset. So if your set is 1, 2, and 3, and B is 1, 2, 3, and Bob, then A is a subset of B. It's both a subset and what's called a proper subset. Both of these are true. Because every element of A, 1, 2, 3, every element of A is found in B. So, yeah. So we say A is a subset of B. And then sometimes it's a little bit weird because, like, technically, like, A is a subset of itself. This is actually true. Because every element in A is in A. And so it's a little weird because in common language, like, B is not a subset of A because A does not have Bob. A is a subset of B, but B is not a subset of A. But A is a subset of A because every element of A is in A. So they introduced the concept of a proper subset, which A is a proper subset of B. That means they're not equal. So B has to be at least one element bigger than A for this to be true. Okay. All right, so here's Aleph Null. I'm sure you guys can all follow this. I don't really need to spend much time on it. It will be on the final. In fact, the final will only be on this slide right here. I thought you said there wasn't a final. That was before I read about the peri-dimensional anabolic continua paradoxa of Cosmos. I mean, you know, It's just it's so much perfect communication. Like I can't not make a final out of it. Yeah, body shadow plane. I don't know. It's something. It's something. Okay, so entering the noosphere, bodiless. Yeah, intuition, matter, analysis, spirit. I don't know what's going on here, but I feel like either stupider or more enlightened. I don't know why there's an orange in the middle either. You guys see this? Like, just like an orange. I don't know. I'm not sure why. Is that the atom of consciousness? I don't know. I don't know how to do it. Do your research. Yeah. We have the Elan Vital and the Ennui Mortel. The ennui brought about by death and the energy brought about by life. I don't know. What is prior to the will dimensionality? I don't know. I honestly have no idea what's going on with this. It's just brilliant or crazy or something. I don't know. Not really sure. Okay. So, to Aleph Null. Aleph Null bottles appear on the wall. Aleph Null bottles appear. If one of those bottles should happen to fall, Aleph Null bottles appear on the wall. All right. So, let's do some set theory. Okay. So we have a set of all these different Marleys out there. You got Bob Marley, Damian Marley, Jacob Marley. And they've got a set of characters from the Christmas Tale. You have Bob and Jacob from the Christmas Tale. Christmas Carol by Charles Dickens. Bob Marley. Okay, so Marley is a subset of Marley. Right, that's sort of trivially true. Every set is a subset of itself. But Marley is not a proper subset of Marley. To be a proper subset, you have to have at least one element more. Marley is a subset of Christmas Carol is false. Marley is not a subset of Christmas Carol is true. And the reason for that is that Bob, Jacob? No, that's wrong. I think I modified this. I must have. Yeah, because no, this is absolutely true. Actually, this is what happens when you get to modify slides and don't put them back. Yeah, this is true, right? You guys see that? Bob is here, Jacob is here, Jacob is here. Therefore, Marley is in fact a proper subset of Christmas Carol because Bob appears in both places, Jacob appears in both places. There's one extra. Oh no, it's not. Never mind. I need more coffee. Sorry about that. Yeah. That's what happens when you stay up all night doing a game jam. No, the slide is correct. Damien is a member of Marley, but it is not a member of Christmas Carol. So Christmas Carol is a subset of Marley, Bob, Jacob, but Marley is not a subset of Christmas Carol because we do not have Damian Marley anywhere in there. Yeah, sorry about that. Okay. Yeah, Marley is a subset of Marley Union Christmas Carol, which I think is just Marley. Okay, so, and there was actually a Bob Marley Christmas Carol, which I don't know what's happening here, but I kind of want to see it. I don't know. Like, why do they have pipes here in the background? Like, I mean, I guess I can get why there's pipes in a Jamaican thing, but I don't know. I'm really sure. It's just like pipes, these guys are like dancing, and this guy, I don't know. Not really sure what's going on. Okay. So what do Bob Marley and Christmas Carol have to do with each other? There's a character named Marley in both of them, right? Like, Jacob Marley. So yeah, that's where I thought I was being original by making a Bob Marley / Jacob Marley joke, but apparently somebody actually wrote an entire play based on it. So yeah, I don't know what to tell you. Okay, so let's go ahead and take a break. This seems like a good pausing time. And let's come back in 10 minutes, and then we'll finish by noon. Okay? So let's come back at 11:05. All right, we're recording again. So one of the easiest ways of thinking about set theory kind of stuff is via Venn diagrams. I'm sure you've all seen these before. We got set A here, set B here. The intersection is just that little area in between where things appear both in A and B. Union is either A or B, but not both exactly. If it's in both, it does appear in the union, but it doesn't appear twice. And that's something that a lot of students make a mistake. If you have 1 and 3 and 3 and 7, 3 doesn't appear twice in the output. It's just 1, 3, and 7. 3's in the set. What else do you want? And you can also do subtraction, A minus B, B minus A. That's you'll see that in like a SQL sometimes. All this kind of stuff you'll actually it's actually really important if you're going to go into databases. Databases are one of the most employable things you can do. So probably talk more about that later. We might do a little day on SQL just because it's so useful. If you want to get a job, learn SQL. It'll take you a day. You get a job. I was offered a job out of high school by my church youth group counselor because I had done a very small amount of work with SQL at that point. And SQL stuff is typically visualized. Yeah, like here's SQL joins. And so these are the different commands you give in SQL to do the different kinds of relationships. Find everything in both A and B, right? So find me all customers that have bought a Nissan intersect with customers that make over 100,000 a year. Okay, and so this will give me, if you find everybody who has a Nissan, everybody who has over 100,000 a year, this will find all the rich people with Nissans. You know what I mean? So. The same as MySQL. Yeah, MySQL is one particular implementation of SQL. It's literally, yeah. I attended a I don't know, community advisory board, I guess you'd call it. Fresno Pacific University was starting up sort of a computer science program, and we could probably talk about that some other time. But basically, you could do 2 years with us at Clovis Community College, and then finish. They have a degree completion program at Fresno Pacific University, specifically in software engineering. And so you can do 2 years here, and then 2 years there, and then you got your bachelor's degree in software engineering. Not computer science, but software engineering is like mostly computer science. It's more or less mostly the same. There's a few classes that are different. And as I was sitting on that advisory board, Simon Sultana, who's a great guy, he's teaching at Reedley now, actually. He's the guy who built the program from the ground up at FPU. He said, all right, industry people, what one skill would you want our graduates to have? And all these people were like, SQL. We can't find enough database people in the Central Valley to do the work that needs to be done. And the owners were like, yeah, a lot of times we give work to each other because our competitor, we literally give work to our competitors because we're so busy. We don't even have enough people. We can't hire enough people. We don't have enough people to do all of the database queries we get. So we actually pass work to our competitors, and they pass work to us, even though we're technically competitors, because there's just not enough people to go around. And if you don't have enough people, then guess what? It's the boss that gets to stay there till 1 o'clock in the morning working on it. And so he's like, please train more people in SQL. And from what I've seen, yeah, it's a pretty good job skill. This is SQL. I've heard so much about it. It's database stuff, But if you think about it, like every major company, and by major I mean like medium-sized and up, like probably a small business doesn't need a SQL database. You know, if you've got 3 customers or something, like you can just remember their names. But for like any company with any size whatsoever, they're going to have some sort of database, some sort of customer relations management, some sort of accounting, some sort of ability to do mailing lists and send flyers and envelopes and things like that. And some of the things will require people to do SQL, and some of it, like, there'll be like a layer on top, and it's just like mail everybody, you know, and you just type in the email, and it handles the low level stuff for you. But yeah, the guy gave an example of, like, he works with the hospitals. This guy that was on the community advisory board, he works with the hospitals here in town, and the federal government will go to the hospital and be like, "Yo, we saw that you got a case of drug-resistant tuberculosis. We would like to know everything about that person." And so the hospital will pull it themselves, be like, "All right, here's the medical record," or whatever. And then the CDC will be like, "All right, so this guy was a farm worker living out in Selma. All right, we would like to find all cases of respiratory disease in farm workers in Selma. You have 24 hours to produce a list of names for us." And so this guy, who is the database consultant for, you know, one of the major hospitals in town, I can't say which, not because I'm under NDA, I just don't remember. And so all of his people were already packed, and so he's like, "All right, I guess I'll just be up late tonight." And so he's like, "All right, query the database, find all records where the person is in Selma and is a farm worker. Set intersection," right? You have the set of everybody that lives in Selma, the set of everybody that's a farm worker. You have an occupation field, and then it selects down, and you sit there and you narrow and you narrow and you narrow and you narrow until you get just the list of names that you're looking for, and then he puts that into a report and sends it on to the CDC, and then the CDC contacts all those people to do screenings and things like that. So it's a thing. It's a really important thing, and pretty much it's one of those skills that is just great for employment purposes. Okay, so you know, if we had Christmas Carol, Bob and Jacob are the Christmas Carol set, and then Marley has Bob, Jacob, and Damian Marley as well. So you can represent a set inside of a set. So you can see that a Christmas Carol is in fact a proper subset of Marley, right? Because it's got Bob and Jacob, both Bob and Jacob are in Marley, and it's got something that's not in Christmas Carol, so it's a proper subset. So if you've got a beaver and you got a duck, the set intersection is a beaver duck, also known as a platypus. And if you've got a guitar and you got a keyboard, the intersection of that is a keytar. I don't know. I'm not sure if the math holds up, but it's kind of funny. Okay, so let's do some... let's just do some examples. I think that's probably the best way forward here. Do like another 10 minutes of class and call it. And then I'll answer questions about the homework, because the homework is due on Tuesday. Let's put together a new page and do, platypus. Let's do some examples. Okay. Set theory, very important stuff. And like I said, set theory is the foundation for modern mathematics, and it's the foundation for SQL queries. And these things are just, kind of have to know it. Okay, so if we have set A, which is the numbers from 1 to 100, we got B, which is all values x, such that x is an integer, and x is less than 10. Okay, the universe is Z. What is A intersect B? Give it a shot. Is 10 less than 10? We got 3 people saying 1 through 10. 1 through 9, yeah. So A intersect B is 1 through 9. Because what is B? B is like an infinite set that goes up to 9, right? So the intersection is going to be 1 through 9, and we write that. Curly braces. Okay, what is A union B? All integers that are either in A or in B. What do you got? Well, let me ask you something. Is negative 10, is that in B? What do you think? Is negative 10 in B? Is 10 an integer that is... Negative 10, is it an integer less than 10? Integers are both positive and negative. Right? Negative 10 is certainly an integer. So is negative 100. So is 100. Yeah. So yeah, negative 10 is a member of B. So A union B is going to be the numbers 1 through 100. Plus all negative numbers plus 0. Negative Aleph Null? No, Aleph Null is not an integer. Aleph Null is not a member of the set. So you would just write this as like ... up to 100, something like that. Or if you did algebra, it'd be like that, something like that. Okay. So all numbers up to 100, all integers up to 100, 100 and less. That's another way of putting it. Yeah, you can't write Aleph Null here. That's not allowed. The size of this set, though, if I asked you what the size of A union B is, what is the size of A union B? How many elements are in this set? Aleph Null, yeah. Some people write infinity. Okay. What is B complement? B complement is what? A? All right, let me ask you this. Is 100 part of B? Is the number 100 part of B? No? So that means it's in B complement, right? What about 200? What about 300? What about 400? None of those are in B, so all of those are in B complement. So B complement is essentially the numbers 10 up. Right? B complement is the numbers 10 and above. The integers 10 and above. So it's also an infinite set. The size of B complement is also Aleph Null. Okay. What about subset? Is B complement, is it a subset of A? B complement's got 10 in it, and 20, and 30, and 40, and 50. It does share some elements with A, but is it completely subsumed by A? Is every element in B in A? Yeah. So... I don't think it goes the other way either. All right, so A is not a subset of B. A is not a subset of B complement. Yeah. Okay. Let's do one more. A is equal to apple, banana, Charlie. B is equal to Jeep, Pinto, apple. What does A intersect B? Yeah, it is Apple. Okay. Samsung, that's funny. Samsung lost the lawsuit a while back for mimicking Apple. Okay. Alright, so that's reasonable. What is A union B? A plus B? Banana. Banana. Apple, banana, Charlie, Jeep, Pinto. Yes. And good, you took out the 2 apples, right? You can only have 1 apple, right? Yeah. So it's going to be Apple, banana, Charlie, Jeep, Pinto. You don't write that twice. So it's these 5 here. Okay. We don't have universe. We can't use complement. Is A a subset of B? Is B a subset of A? No. So that's it. That's set theory. Yep. So just remember the size of an infinite set is Aleph Null. That's the one tricky bit. So if you ever are asked how many elements are in a set from 1 to infinity, the answer is Aleph Null. Okay, that's our class for today. That's the basics of set theory. We will pick it up again on Tuesday, and I will now stop the recording. If you have any questions about the hash table assignment, now's your opportunity. Otherwise, I will see you guys on Tuesday. Peace out.